Okay, our next speaker is Frederic Jacobs, who works at the Swiss Institute of Technology. And by night, he builds and breaks security software. And he has been leading the development of Open Whisper Systems' secure messaging app Signal, which provides end-to-end encrypted text messages and phone calls. And nobody leaves this room without installing Signal on their phone. Seriously. Have fun.
Thanks. Well, sorry to disappoint, but I'm not going to talk about Signal today. So I heard someone is presenting a man-in-the-middle attack on TechSecure. So I thought, well, somebody is already going to talk about the TechSecure protocol, so I'm going to present something else. And I usually work on like security software. I like to write some code, and you know Signal, but there's also this new project called IT-SeCX that is being worked on. Both are open source software, and IT-SeCX is a full proxying client on iOS to use the Tor network. So the goal is to be able to proxy the entire content of your phone through Tor. It's still being worked on. It was only possible since iOS 9, because before that Apple didn't open up the networking APIs. But now we got started on this, and if you want to help, we're implementing it in Rust, and yeah, help is always appreciated. So the content of this talk is based on a blog post I did, because with iOS 9, people were asking if we were going to enable Bitcode. And I said no, and I enumerated a few reasons why. The goal of this talk is really understanding the impact of Bitcode on the distribution of iOS security-sensitive software, but not only. I'm going to talk about like software distribution in general, as Morgan puts it, it's really about securing your supply chain, right? Because you want to make sure that the code that people run on their phones is really what you wrote and what was available on GitHub. So the outline of the talk, first talk a little about software distribution, then we're going to talk about what changes with new versions and how Apple wants us to distribute software now. And then we're going to talk about like the security implications of these changes. So software distribution is crucial when you think about security software, because you can have the best app possible if you're not distributing it securely, if you're installing code from the internet. Like Android got in a big mess by letting like regular users just like download the APKs over HTTP and install their stuff. And having a software distribution strategy is really important. But we're at this point where the app stores promised us security, but we didn't get this security. We just got like a huge black box that we cannot control, and backdoor the binaries are getting on there. There was XcodeGhost recently that made the headlines. Software distribution these days, like we have a developer who writes some code and then he decides to build it with, in the case of like iOS, and we're going only to focus on iOS in this talk, he compiles it, and then whatever happens next, he has no control over. He puts it into this black box that is the App Store, and next thing he sees is like some users download the app, and he can eventually download his own app and see if the code is matching, only if he has a jailbroken device. So of course I put this black box there, but I don't know how it works at the inside because it's a black box. But what we do know is that I have an interface, I upload some stuff that's called iTunes Connect. Apple applies some DRM on it, so they have this anti-piracy modification that they do to your binary. They resign your binary, and then they put it somewhere, and that's where users are going to download it through the App Store. If you're not familiar with iOS in general, this is what a binary outline looks like. There are multiple sections. You have load commands, and then you have segments and sections. The important thing to remember here is that there can be multiple parts in a binary that will fulfill different functions. And in the case of Bitcode, the fact that the Mac-O binary, which is used on iOS and on the Mac, is structured this way will be important. So we'll see more on that. If you're interested into the Mac-O binary, I encourage you to read Ange Albertini's posters that he explains how these binaries are laid out, and he's doing this for multiple file formats. It's really well done. Another thing you need to know is what fat binary is. Like, they're called universal binaries. This is just a binary structure where you have some headers. The headers are like defining what architectures this binary can run on, and the header also says, hey, if you're going to run it on a ARM64 device, you should probably like start reading this binary at this offset. You can look them up with a few commands. So you can do otool -f and then like read the headers of the fat format, and it will return the number of architectures, and it will return the fat magic that helps the machine to know what the endianness of the device is, and if it's like 32 bits or 64 bits. When you think about software distribution, this is really important because Apple changes like their hardware and their like system on chip quite frequently, and they want to maintain like, and they want your apps to run on like older devices, and they want to maintain still a few iOS versions, even though like there was a new processor that comes out. They want developers to be able to build binaries that will still run on older devices at a low cost. So these binaries, these fat binaries, they have some advantages. You can build your app and it will run like on multiple microarchitectures, and you only have to build one single file and distribute this file. So that's pretty cool, especially if you think of the previous like app distribution model where people were downloading some zip file from the internet and they were installing their Mac app by drag and dropping it into a folder. You don't want to ask users, hey, before downloading this file, what is your architecture you're running on? And then also if they move to a Mac that has a newer architecture, they can just like move their files and they don't need to re-download all their apps. So it works well with like backup and restore. But then of course, there's a reason they're called fat. It's because, yeah, they take up a lot of space. So adding architectures comes at a huge cost. And this is the reason why with iOS 9, Apple thought, hey, we're going to do something about binaries and we're going to like strip the architectures that are not needed to run. And so this way they introduced app thinning. So the goal is to reduce like the app download size, and app thinning just looks and compiles different versions saying, hey, if it's going to run on this specific iPhone, you need a given screen resolution. So I'm only taking these assets. And then this iPhone has 64-bit ARM processor, so there's only one architecture that Xcode builds that is required on this device, so let's pack it with this. And then it strips all the unnecessary assets. This doesn't involve recompilation. Okay, so let's get into Bitcode and see what this does. So let's quickly review the Bitcode, the LLVM compiling process. You have a front end, which is like Clang in the case of like C, C++, Objective-C, that takes your file here. It's a simple like C hello world. It compiles it. It generates something that is called LLVM-IR, and that's like the intermediate representation for LLVM. And initially, people thought that like, this is great. So we're going to have a compiler that has a front end that takes something from a language. It generates like an intermediate representation that is kind of like supposed to be retargetable, and then you can like take a given front end, build some code, have all your optimizations on an intermediate language, and then like compile to the backend, and you can like build a front end that parses a new language, let's say Java, and then you have this optimization process that's shared because that's where compilers cost a lot of money to develop, and then you can have like the backend you already wrote for another programming language that could be used. But if you're looking at this, there's kind of something that doesn't seem really retargetable there. It does specify a specific target and a target architecture. So why are they mentioning a target if like LLVM is supposed to be able to target your binaries, to retarget the ER, sorry. So the issue is that unlike what LLVM wanted to be or what people thought it was, LLVM-IR is not target independent. And the reason for that is because, especially on iOS, the languages that are going to be parsed, their semantics are really not designed for target independence. You have types that assume stuff about what the hardware actually is made of, and you have undefined behavior that is not specified in the specification, and that is like really open to the hardware implementer to define. So LLVM-IR is really not what people hoped it was. Then when the code is in ER form, it gets compiled later on by the backend, and that generates like a specific target binary. The target is optimized, and like the code generator generates like what you would expect a good application to run based on this ER. But again, since the ER depends on a given architecture, you might have you can only generate something that shares the an ISA that's quite close to the one that was in the ER. So what did Apple introduce in iOS 9? It's called Bitcode recompilation. So Bitcode as a format is nothing new. It was already present in the LLVM project for a while, but Apple took advantage of it to design a new system where they say, okay, if we're like releasing a new Apple Watch and we want to change processor, we don't have to wait for like all the developers to rebuild their apps. So it doesn't give them the freedom to like design a new processor completely from scratch that doesn't have like the same ISA, but it's just like it gives them some level of freedom for micro architectures optimizations. It's completely separate from app tending. Like you can have your binary that is stripped from unnecessary architectures without having it to recompile. So currently how it's implemented, and this is like some reverse engineering work that I did over the past few months is they're like generating these like fat archives, like a regular binary, with multiple architectures. So it's pretty much a usual binary that you would upload to iTunes Connect. It doesn't have any strangeness. It could still run on any device. But if you're looking more closely, it has like special Mac OS segments. So these were like the segments of the binary that you could have with like different load commands. And these LLVM segments contain a section that starts with bundle. And in there is something called XOR archive. So it's just a packed version that contains like one LLVM bitcode file per class. Okay. So there's a project on GitHub that's called Bitcode Retriever, and that's really useful. That scans a given binary, it looks at all the architectures, and every time there's like a LLVM segment, it dumps the bitcode out of it. You can then like unxor it, and you get the bitcode that you can then read the human readable version, which is the LLVM-IR, because bitcode is just like some bit stream of LLVM-IR. Okay, so good. Symbolication. Because Apple is like taking your app and recompiling it, you might lose symbols, and this is quite strange when you think about it, because it was completely broken on day one, and developers had crashes, and they were getting these like crash logs from Apple, but they couldn't like apply the symbols on it because something screwed up in like Apple's backend, and suddenly like they couldn't read their own like crash logs. This is quite problematic. If you have a bug and you cannot like, you can just like read some addresses that don't have any meaning because you don't have the binary, you have a problem somewhere in your supply chain, right? Thankfully, up to now, you can still opt out for iOS binaries, but it's mandatory for tvOS and their WatchOS stuff. So a few issues with like turning it on are obviously that like if Apple enables new optimizations because they changed the version of like LLVM they're using, you cannot reproduce this build locally. You have like very little information about debugging. You're just like, oh great, I uploaded my intermediate representation and now I'm stuck because whatever binary it generates, I'm unable to like understand what kind of optimization is going on. And they may like do it automatically. They say, hey, we might just suddenly decide to recompile your app. So what are the security implications? I think first we should look at all the compiler optimizations and the correctness of these optimizations. A lot of this topic has already been studied by people in language security, and this is based on a paper I reference later, where you have classes of issues with compiler optimizations where people think, hey, we're gonna prove that like people designing programming languages or optimizations for their compilers saying, hey, we're going to design this optimization, and they're proving it on a theoretical machine. So they're not proving it on like ARM or x86. And so most of these optimizations, if you think on a machine, you have like a virtual representation, but you don't have to take into account what stays in the registry and whatever. These optimizations are correct, but as we'll see, they're quite problematic in real life. So the first class of like vulnerabilities is persistent state. You don't want some state of the application to remain there even though the developer thinks it's gone. So the developer thinks, hey, like this encryption key is gone, but actually it's still there. It's still there in memory. And someone who gets allocated this memory, or someone who has an exploit and can run something, some code, can steal it from memory. So there are different classes of persistent state vulnerabilities. The first one is dead store elimination. We'll see an example of this one later. So you store something, but then you never access it. So the compiler thinks, oh, he's storing something, but never uses it. So it's useless. We really shouldn't like do this command because it's a useless store. So dead store elimination is just like, oh, let's remove this code because it's actually useless. But we'll see for some reasons it might not be that useless. Then there's like function call inlining. It's the compiler thinking, hey, this small function, instead of calling it, we can just like inline it into the caller. So the callee method is like incorporated, and you thought that the execution space of your method was secure, but suddenly it's like exposed, like your, for instance, the encryption keys you have are exposed to a way wider attack surface. And then there's code motion. It's the compiler thinking, hey, we're doing these like multiple these multiple computations. It would be a great optimization to move some code around because it has no dependency. We can just like move this code around and it breaks your logic that you thought was there to eliminate persistent state. So here's an example of dead store elimination. What happens is that you have a password that's in memory, and at some point you say, oh, I don't need this password anymore. I should wipe it from memory because I don't want an attacker that has access to my memory or that compromises my program to have access to it. So I'm just going to zeroize it and like fill this area in memory with zeros, and everything will be fine, right? But that's not how the compiler thinks. The compiler sees like, oh, he's like trying to put some zeros in there, but then he never reads these zeros. Like this developer just puts something there and I don't see the purpose for it, so he removes it. Some compilers with some flags give you warnings about all these issues, but sometimes they don't. There are a few techniques to prevent this optimization to happen. You can set the variable as volatile. This should prevent any optimizations on it. Microsoft also has in its libraries a method called secure zero memory that prevents this optimization to happen. Yeah. Okay. Function inlining, same thing. You have your method that takes the next message on the network, and you consider that this is potentially exploitable or something, or it's not run in a secure environment, so you would worry about this. It calls the decrypt method, but the decrypt method is small enough that the compiler thinks, oh, I can do all of these instructions inline at exactly in the next message method, and suddenly if it fetches the decryption key, and the decryption key was in the stack frame that was considered to be secure because it's a stack frame from the decrypt function. This decryption key is suddenly exposed to the entire scope of the next message function, and this is a potential security issue, or makes it easier for an attacker to exploit. Then there's a whole other range of issues with undefined behavior. You might say, hey, there are things not defined in the C programming language, and things that the C programming language doesn't define because it wanted to be portable and it wanted to leave some optimizations to the hardware implementers. And so all of the things I'm enumerating there, like in C, uninitialized variables and like dividing by zero can have undefined behavior. Other issue very close to my heart because it affects crypto are side channels. A lot of side channels are exploitable due to compiler optimizations where the compiler doesn't understand some of the requirements from crypto people. So what is a side channel? It's like you can find out things due to some implementation condition, for instance, like time and energy can help an attacker to infer some stuff about secret material that can later be used to exploit your encryption scheme. So, for instance, one of the things you want in some cases when you're doing computations is constant time. And especially if you're branching on secret material, you don't want to have someone who's just looking at how long the requests take get any intuition about the path being taken. So crypto implementers might write something like this, where they have operations at the top, and then that take a certain number of instructions, and then they think, oh, I should probably put the same amount of instructions on the other branch so that it's going to take the same time to run. But then the compiler sees this and he's like, oh, silly developer. Why are you writing 3 lines of code when you can only write 2, right? So it sees that this is like replaceable by what is on the right. So it does this, but then you're changing the number of instructions that are required to compute this in the second branch. And this leads to a timing attack, because you know that, oh, if it's taking less time, then it's probably branching on this second thing. Okay, so these are issues that arise from the fact that Bitcode performs a bunch of optimizations, and you cannot opt out of these optimizations if you're using Bitcode. And they lead to all these like potential issues in crypto libraries, or in other code, right? So another thing is you might say, okay, so how do I get control over these side channels? How do I get control over this undefined behavior? Well, you would use inline assembly, but sadly, Apple doesn't let you do that. And you might say, okay, well, it doesn't matter because who wants to write assembly? For multiple reasons, mostly performance and control over timing. These are key components in cryptographic implementations. I see I need to speed up, so I might skip some slides. The other issue with Bitcode potentially, and it's not only limited for Bitcode, but it becomes way more important with Bitcode, is how much do you trust the compiler? And the compiler is going to be like even more important when you are going to have one single compiler for all the App Store apps, because Apple is going to rebuild all of these like apps in the cloud. So there was XcodeGhost. You could like have issues in your security supply chain where libraries are replaced, and there's this like very popular dependency manager for iOS apps called CocoaPods, and a single bad line in there could compromise the entire security of your application. Okay, you could have compiler bugs and a buggy compiler or an environment. Okay, so potential for backdoor injection. The Obama administration had a working group on the issues with encryption and how to undermine encryption if they need access to some, let's say, terrorists, but that's debatable. They need access to some communications. They could say, okay, we're gonna like push an update compromise a binary of an encryption app to put a backdoor in there and abuse the automatic update system to be able to disable some encryption features, for instance. Okay, and then finally, all of these issues that we said about like the compiler trust and the issues with Apple being coerced by some state to do something are even more a problem on iOS than on any other operating system. It's because users have so little control over verifying builds and knowing if what they're running on their iPhone is really what was on the App Store. So to verify builds without Bitcode, you already need a jailbroken device, start the app, dump it with LLDB to remove the DRM. Otherwise, Apple encrypts the binaries that you're downloading from iTunes, so even the developer cannot verify it, and you cannot opt out of DRM. Okay, so this is already quite bad, but then with Bitcode, they recompile your app. It's not going to match whatever you compile locally, probably. So it's just like, okay, now I have these two different binaries. What can I do? And depending on what kind of optimizations they turn on and what kind of like code modifications they're doing in the backend, you cannot know if this is like hostile behavior or just some really nice optimizations that Apple is doing to make your app run faster. Okay, so just to wrap up, Apple is doing some work to have like some real target independence. They announced this week at the LLVM dev meeting the Swift intermediate language. The goal is to have a higher level ER to be able to retarget the ER to completely new architectures. It's reducing undefined behavior by having only Swift as a front end, and ERGen handles like type lowering and concretization of the target. Okay, so any questions? I'll put my slides online, and there's like a bunch of references if you're interested in any of these topics. Thanks. No. So when you're building your app with Bitcode, it compiles the binary like usual. So it would build a fat binary, exactly containing like all of the targeted infrastructure, like it would do before iOS 9. What it does is that for each architecture, it embeds the Bitcode into it. And so it does provide a binary. But Apple says, hey, we may recompile your app at any time. So you have no guarantees that even the architectures you submitted will not be optimized later on.
Can I ask a completely unrelated question?
Sure.
With WhatsOS, with the XcodeGhost protocol, you
Yeah.
verification will never come to the users?
Which will what?
Fingerprint verification.
Well, it's present in Signal.
Yeah, in Signal, but I mean the implementation of the XcodeGhost protocol in WhatsApp.
We'll take this offline. Sorry.